Hello everyone again. In this lecture we are going to introduce a very important concept, the concept of the second moment of area, sometimes or often also called moment of inertia. So in order to do so, let's look a little back and recall the concept of the first moment of area. And I'm going to illustrate that with a simple diagram in which, for example, we have a flat area of total area A, and we can calculate the first moment of area with regard to some axis, an arbitrary axis. And the way we did that was by dividing the area into an infinite number of very, very small elemental elements, dAI, and then we were able to calculate the moments of these areas, so multiply by these elemental areas by their moment arms with regard to the arbitrary axis that we selected, yi. And then we could use this property to determine the location of the centroid, y bar, by also multiplying this moment arm by the total area of the plate. So in other words, we were writing an equation in this format: dA1y1 plus dA2y2 plus dA3y3 plus many other terms like that equals to A times y bar. And from here we could use these summations and convert them into an integral and determine the first moment of area about the arbitrary axis. Once we have done that, we could solve for y bar, which is the coordinate of the centroid of area A, as integral over the area of y dA divided by the total area. So now we can apply this principle to an example and see how we can use this concept. So let's consider a rectangular area like so. The dimension of this area are d in the vertical direction and b horizontally. And in order to express the integral, we select an arbitrary axis, let's say the purple one, from where we're going to measure the y coordinates in the upper direction, as well as a very narrow, infinitesimally narrow element of width dy located at a distance y from the arbitrary axis. So then A times y bar equals, of course, to the integral. Now we can go into one dimension only, so from 0 to d. We do that because the width is constant of y b dy being the area. So that equals to by squared by 2 taken from 0 to d. Or in other words, we can solve from y bar from here, and that will be equal to, guess what? D over 2, right in the middle, and that's the location where we already expected that the centroid of a rectangular area would lie, in the middle of its depth, half d. Now, that was based on the concept of the first moment of area. Now let's talk about the second moment of area. And this, by definition, is in fact multiplying the area, the elemental elements of the area by their moment arm twice. So in other words, the second moment of area about the x-axis will be equal to integral over the area of y squared dA. And this will have to be calculated about the centroidal axis. That's a major difference from the first moment of area, because now the area has to be calculated about a specific axis, which is the centroidal axis, not just about any axis. Similarly, the second moment of area about the y-axis equals to the integral over the area of x squared dA. So these are important formulae that express the way the second moment of area is derived and calculated. Now, you don't need to really memorize these integrals because we will not use them in practical examples, but you need to understand how the formulae that we're going to derive in this example came about. So let's do an example with a similar rectangular area as before. However, now we're going to move the axis to the middle. So this is indeed the centroidal axis of this rectangular area. And this area has a width equal to b and a depth equal to d. So the distance from the top to the centroidal axis is half d, as is the distance from the centroidal axis to the bottom of the section, also half d. We're going to select an element which is infinitesimally thick, or thin really. So its width is dy, and the element is located as a distance y measured from the centroidal axis in the y direction. So now if we were to calculate the second moment of the area about the x-axis, the horizontal axis, which is the centroidal axis, that will be equal to integral over the area of y squared dA, or if we go in one dimension, integral from negative half d to positive half d of y squared b dy being equal to dA, and that equals to by cubed divided by 3, taken from negative half d to positive half d, or b over 3 times d cubed divided by 8 minus negative d cubed divided by 8, or b over 3 d cubed divided by 4. In other words, the second moment of area for a rectangular area equals to bd cubed divided by 12. This is an important formula that you must remember, and also know that the dimension that is cubed is the one that is perpendicular to the centroidal axis about which we calculate the second moment of area. So always that dimension is cubed, the one that is perpendicular to the centroidal axis about which the second moment area is calculated. So let's look a little in more detail at rectangular areas and calculate the second moment of area for a rectangular area, right? So bd cubed divided by 12. Now note, as I mentioned at the beginning, often and especially in practice, the second moment of area is called by people the moment of inertia. And I put quotation marks for inertia because inertia is related to dynamics and there's nothing about dynamics here. But this is how it's called in jargon. So the second moment of area often is called the moment of inertia. It means the same thing, really. So look at this rectangular section. It's taller than it's wide. So its width, we can call it again b. Let's call the depth h. And the two centroidal axes are x horizontally and y vertically. So they both go through the middle of the section in either direction. Now, if we make the assumption that h is larger or equal to b, and then we can calculate ix as bh cubed divided by 12, right? H is cubed because it's perpendicular to the x-axis, and iy equals to hb cubed divided by 12, b being cubed because it's perpendicular to the y-axis. And then ix will be larger or equal than iy because h was larger or equal than b. So therefore, by convention, we will always assume it's a convention that h is larger than b, so hence always ix will be larger or equal to iy. Therefore, we call the x-axis the strong axis of a section because it leads to a larger value for ix, and the y-axis the weak axis of the section because it leads to a smaller value for iy. And this is always the case by convention. Always ix is larger or equal to iy. But now what happens if we have a similar section, but this section is rotated? So now the vertical direction is the smaller direction, and the horizontal direction is the larger direction. You may notice that I kept the notation such that h is always larger or equal to b. So in order to maintain the convention that ix is larger or equal to iy, we always must rotate the axes with a section. So as you can see, the x-axis now becomes vertical and the y-axis becomes horizontal because we have rotated them with a section. So axes are always glued to the section. They rotate with a section. So therefore, always, regardless of the configuration of the section, ix, the moment of inertia for the x-axis, will be larger than the moment of inertia for the y-axis, and x will stay the strong axis and y will stay the weak axis. So thank you very much for watching this lecture. We will learn about another concept, the parallel axis theorem, in the next one.